Hi all, thank you for joining my channel today. When talking to people about my work as a scientist, I often get the feeling that people don't really understand the whole process of science. I'm not necessarily talking about the scientific method per se, but more about what the experience is like to come up with a hypothesis, testing it, and then publishing the results. It may sound straightforward, and in theory it is. But there are checks and balances in place to ensure that what is published is really correct and it really checks out. Many people appear to be under the impression that as a scientist you spend lots of time in an office with a whiteboard covered in equations and then you go to the lab to do a quick test. And once you have everything, you quickly write it up and approach the press with your result. Again, in broad strokes, this is roughly true. But it fails to convey the amount of work that actually goes into this. I recently worked on a paper which was published in a very prestigious journal, and I will go through my experience and describe the whole process without giving any details on the paper or the experiments. This is because the experiments are difficult to explain and won't really add anything to the narrative. In addition, the experiments are pretty unique at this stage, so describing them would make it very easy for you to identify me and my institution, and I would essentially be doxing myself. Now what we did is make a thing and measured it to see whether it would allow us to study quantum effects on a mesoscopic scale, and it worked. To determine this, we needed to fabricate an object, measure it using optical microscopy, electron microscopy, atomic force microscopy, and magnetic force microscopy. In parallel, we performed other optical experiments, numerical simulation, and elemental analysis using energy dispersive X-rays. Now, to do all of this, the first thing that was needed was money to buy the equipment. Now, considering that one single lens in our optical microscope costs around $5,000, we needed a lot of money. There are 6 lenses in that microscope. Over the course of a couple of years, our principal investigator applied for grants to secure this money, and this is straight away where the first problem comes in. To be awarded grants of this size, you need to demonstrate that there's a strong likelihood that you can achieve your objectives. However, to demonstrate this, you need money for equipment. As scientists, we can't just say that we reckon that something is going to work and then lots of money will be thrown at us. Science budgets are extremely small and the politics of this can get rather nasty. However, once the grant came in, the group spent a couple of years building the equipment and testing it. Now, some equipment was commercially sold as a whole and it just needed calibration and acceptance testing, which only took a few months. At this point, we could start making simple things to test whether the equipment was going to give reproducible results. We started with simple things and then compared our physical measurements with some simulations. The simulations themselves were quite difficult on their own. We had access to some open source software which allowed us to perform these calculations on simple objects based on the theory. This allowed us to form hypotheses, test them theoretically, and then finally test them using physical experiments. But we quickly realized that even our top specification desktop computers couldn't handle the calculations. We had to rewrite the software so it would work on a supercomputer. This then required more acceptance testing to make sure that the adapted software still produced the same results as before. This also took about 6 months, but now we can easily perform calculations which require up to a terabyte of memory. Now, being good scientists, we then implemented another type of simulation software which works differently to make sure that we get the same results from both methods of simulation. At this point, we are a few years down the line from the conception of the original idea, and we have only tested the equipment and made sure that it can reproduce well-known results. We now had to figure out how to make the structures that we wanted to make, and although the design was not easy, it was relatively quick to make a thing. However, to make a good thing took the best part of a year. But remember that we have to compare our results against simulations. We could base our simulations on the design, but that assumes that the fabrication method is perfect, so we have to characterize the product to define the parameters of the simulation properly. We had to use scanning electron microscopes to get a good picture of these things and then perform energy dispersive X-ray spectroscopy to make sure that the things were actually made of the materials that we expect them to be made of. Now we had an idea of the simulation parameters, we could calculate the expected results for different measurements and compare them to the physical measurements. One of the biggest challenges we faced was that our measurement techniques were not designed to measure these types of structures that we were measuring. And actually, one of the big breakthroughs we made was demonstrating that it was possible to perform these measurements, and we got results that matched the theory. Now, we spent a few months on each measurement type. Once we had performed measurements, we changed the parameters of the measurements so we could see if we still get similar results, which we did. Once we had captured what we wanted, we did something that may seem strange to some people. We started again. We wanted to be 100% sure that what we observed was actually there and not a fluke. Once we repeated the observations a few times, we then tested them a bit further. If we were really seeing what we were seeing, then we should have been able to manipulate the system to get predictable behaviors which would otherwise not be possible. So we spent a few more months on this to be confident that we were correct. And after having done these sanity checks, we then approached some trusted colleagues who do not have a vested interest in our work to comment and critique our results. We then addressed their concerns and grew increasingly confident in our results. And at this point, we felt that we were ready for publication. Now, whilst you're performing the experiments, you start getting an idea of what the narrative of the publication is going to be. Unfortunately, when writing, it is rarely as straightforward as you previously thought. As you are writing, you come across little things that you feel are missing, so you go back into the lab and test these little things. Some are easy and can be sorted in half an hour. Some can take weeks and can make you seriously question your observations and your own competence. You then go through proofreading. Now, this is not some college essay that you quickly read through to make sure that you haven't misspelt anything, because actually incorrect spelling is quite forgivable. Now, you check that everything you say is accurate and consistent. You try to preempt what the reviewers are going to say, and you try to address these things before sending it off. Once you have finished your write-up and submitted it to a journal, you get to a truly harrowing stage. An editor reads your work and determines whether your work is deemed important enough and on topic for their journal. Now, once they've made a decision, you either get rejected outright, or you get passed on to peer review. Now, at this stage, there are 2 or 3 experts in your field that check your paper for quality, but make no mistake, academia is brutal. These people are probably not your friends. In fact, they are often your competitors, and some will do everything in their power to stop your paper from being published. But their powers are limited to questioning the methodology, and they will erect hurdles for you to jump over in the hope that you won't address these concerns and your paper is rejected. Now, if you can jump over these hurdles, then your paper will go through publication. This review process can be lengthy. It took us about 6 months. Some objections raised by the reviewers were valid, but others were clear attempts to block publication by setting ridiculous standards. Now, at this point, we went back to the measurements and the fabrication, and we repeated everything with their objections in mind. And the result was actually high-quality scientific evidence. And the reviewers who attempted to block the paper then admitted defeat and approved it for publication. Now, people think that the scientific community spend a lot of time backslapping and congratulating each other on their brilliance. This is never the case. I have been fortunate enough to work in departments with a strong collaborative culture, but the moment you step out into the wider world and present your work at conferences or submit to peer review, everything changes. When presenting your work, and even within your own department, the climate instantly becomes adversarial. Your work becomes a target for criticism and everyone tries to piss on it. And if it comes out dry on the other side, then you have done good work. Now, this culture sounds very difficult to deal with, as it can make you feel very vulnerable. An academic career is definitely not for the weak-minded, but this culture is necessary. If we act all buddy-buddy at conferences and during the peer review process, bad science is produced. And unfortunately, this has happened. One example is Andrew Wakefield's paper linking MMR vaccines to autism. The peer review process failed here. Now, this paper was published and the result has been extremely dangerous, and it resulted in the anti-vax movement. Of course, the peer review process is not the end. It is then up to the scientific community to evaluate the work and try to repeat the work described in the paper. In the case of Andrew Wakefield, the scientific community quickly smelt the bullshit and exposed the flaws in the study, which eventually resulted in Wakefield being completely discredited and eventually blacklisted for scientific misconduct. But Andrew Wakefield is really a topic for a different video. I hope that this long monologue has shed some light on the long process of performing experiments and what work lies behind a paper that is published. In our paper, we demonstrated some really cool stuff, but it really is only our opening gambit. We have opened new possibilities for research but into both fundamental physics and applied physics, which will result in significant technological advances in the next few decades. But anyway, that's it from me for now. In the next video, I will probably look at something a bit more silly, but please like and subscribe if you want to hear more of my thoughts or hear me science the shit out of some stuff. So until next time.